All right. On Thursday, we are going to discuss Riemannian geometry, or this is just purely kinetic Lagrangians, as this was uh, titled in um, David Tong's lectures. And we are going to talk about the particle and electromagnetic field. Okay, so we will start with Riemannian geometry. By the way, about the Kepler's problems, Kepler's laws, for these, I just posted a very detailed PDF file on Moodle. Please take a look at Moodle. This is somewhat tangential to our discussion, but nonetheless, I think it is pretty insightful of how you can already use some solutions that we obtained in the past. In this case, it's two-body problem, to actually draw some conclusions about, the planetary motion, for example. All right, so here we are going to discuss Riemannian geometry, and we are going to consider purely kinetic Lagrangian. So in this case, it will have only the derivative with respect to time of the generalized coordinates q and qb. Okay, very good. So, but now since it's Riemannian geometry, I can have a non-trivial metric, okay, which is given by this matrix, defined by this matrix GAB, which in general is a function of a generalized coordinate itself. And in a sense, we had already this type of Lagrangians before, right? Whenever we transform our Cartesian system to the polar or spherical coordinates, we also actually have this non-trivial matrix. We just write this as a collection of terms, right? So we just write this equation as just a collection of terms. But by all means, the summation with respect to A and B here is implied. Okay, this is just most generic case where GABs might be quite non-trivial. Okay, but any means, I mean, so this type of the problems is just more abstract a form of what we did already before. Okay, so now, I would like to find for this Lagrangian, I would like to find the equations of motion. For this, I would first, deal with the first term in the Lagrangian, right? So this term. So I will first find dl dqc dot. Well, this is pretty straightforward to find. I have to differentiate this part. The only pieces that depend on the velocities are here. I will get a factor of 2 because there are two factors of the velocity. These factors of 2 will cancel 1/2 in front of it. And at the end of the day, I will get this equation. And again, so if you are uncomfortable with this calculation, please do this once more, because the Kronecker delta function enters somewhere in the intermediate steps here, okay? And then I simplified. But once you get enough intuition of how to do this, you can just immediately write this equation and this equality by just looking at the Lagrangian and the derivative. Okay, but again, so if you are not comfortable in doing this type of calculations, please perform these. So this can be expanded here, in multiple steps. All right, so again, so I'm not going to do that. I think we did it enough during your first, zeros homework. So, but I do encourage you to repeat if you feel not confident in this type of manipulations. Well, the next step for me is to take the time derivative of this combination. Well, when I can differentiate the second term, that's what I get here, right? And I can also differentiate this matrix GAC, okay? It can be differentiated with respect to the coordinate QB, but QB itself depends on time, and therefore I will have here this combination, right? Its derivative with respect to the QB, so dB equals to dQB, okay? And I then differentiate QB with respect to time. Okay, very good. Now I would like to play with the second term a little bit, Because you see, so the a second factor here, okay, not the second factor, these two factors here at the end are explicitly symmetric with respect to A and B, while where the prefactor is not explicitly symmetric. Whenever this arises, it's easier, it suggests that it would be easier to symmetrize this part too, okay? And this is exactly what I did. I just split this term into two pieces, okay, with a factor of 1/2. And after that, I relabeled some indices to get this final result. But by any means, so this is just equals that. And you can prove this by operating with dummy indices. As I said in the past, I'm not going to go through this in detail. I hope you are confident with manipulating the dummy indices and proving such form of identities. I do expect you to be really good at it. Okay, well, after all this done, I'm just going to substitute this equation into my Lagrange equation, okay, and I also will compute this part, which is kind of straightforward because for this yellow term, the only thing it acts on is the actual matrix GAB, right? The rest of this is just velocities, so it's very simple to write. Okay, I substitute everything here, and okay, and then equate it to 0, a little bit simplified the collected the factors and simplified this a little bit. Okay, so when I did the simplifications, I did one can use this fact that GAC is the same as GCA because you remember G was a symmetric and actually invertible matrix. So to proceed further, looking at this equation over here, how would I actually solve it? Well, most likely I need to solve it for the acceleration, right? For Q double dot. So how to do this? Well, so this is kind of a linear equation with respect to the accelerations, right? We have multiple accelerations. This is a matrix, so it's a linear equation with respect to accelerations. So what we want to do is we want to solve this linear equation, but we can solve this. Okay, so in general, it has the following form. It's a matrix A times vector Q double dot, okay, vector in this A space, like with respect to this index A, equals to B. Well, I'm going to multiply both sides by the negative. Both sides multiply from the left by the inverse matrix A, right? Then I will get here the unit matrix on the left hand side, Q double dot, and on the right hand side I'm going to get A to the negative first power times B. So this is some vector, so let's call it little b. Okay, and that's it. So this will be the solution. And so we're the same we are going to do here. We are going to multiply both sides by the inverse of this matrix G. Okay, and the inverse of this matrix G, so that's going to be inverse. I'm going to denote by G these upper indices. Okay, so this is just notation here. I'm going to introduce this notation here. This is a commonly accepted one. Okay, so in this notation, the fact that GDC is inverse of GCA is just given by this equation. Okay, so this is just matrix. So what is written here is, let's use G to the negative first times G equals unit matrix. Okay, that's equivalent. All right, well, when I do that, okay, so a new term will appear over here. You remember that this is how we get here. So a new term appeared, and a new factor appeared over here. This inverse matrix, which I multiplied everything by. And this guy here now doesn't have any matrices in front of it. And this is my final result for the equation of motion. Okay, sometimes we also introduce this notation gamma for this combination over here. It's called Christoffel symbols. Christoffel symbols. Okay, and it all multiplies this velocity and it equals to 0. So very straightforward, nice equations, nice looking equations. And they are true for any Riemannian geometry, and we have Lagrangian, which contains only the kinetic term. So this is also called geodesic equation. So why do we call it geodesic equation? Because if you consider in Riemannian geometry, if you consider the length of the of a line, okay, with fixed points, okay, then it will be given. Well, we already dealt with that. It's ds, okay, and ds is given in well, before, when we dealt with just two-dimensional system, you remember that it's going to be given by dx squared plus dy squared. But when we have Riemannian geometry, we will have a little bit more complex construction, or something like this, right? So where G is this metric tensor, this matrix, symmetric invertible matrix. Okay, so we can take the square root, we obtain this. I can also pull out the factor of time from this equation, then I will get the velocities over here, q dots, qa dot, qb dot. Okay, so and therefore the length of this curve, okay, will be given by this combination. So this is gab. Okay, by this combination. Oh, well, and this is what I want to vary, right? So, but let's do this action. Okay, this an analog of action. Okay, and would like to vary this to find the shortest path between 2 points in Riemannian, geometry. Okay, I'm going to vary this, and when I vary the square root, it will just give me the variation of this factor divided by the square root. And this square root over here, which appears over here, I can now absorb into the definition of my time. Okay, and this is what I've done here. I absorbed into the definition of the time. And this part I will just call the Lagrangian, GAP. This I will call the Lagrangian with which we started in the very beginning. Okay, and so why I'm showing this? Well, I'm showing this because this procedure would define the shortest path between 2 points in Riemannian geometry, and this is the same Lagrangian as we started with, and this is why the corresponding equation which defines the path or the curve between these two fixed points is called a geodesic equation. Geodesic equation because it defines the shortest path in the Riemannian geometry.